Hello everyone and welcome back for a lecture uh, on topic design of EOT crane. In a previous lecture, we was discussed about the design of EOT, problem number 2, where we have finished the design till rope wire design and hook design. Now in this lecture, we will discuss the further designs. So right now we are going to design third part, design of cross piece with the side plates. This cause in a hook snatch block assembly, the crosspiece is the part where the hook is going to be mount. uh, in this region, the hook bearing is going to be mounted, and the hook upper portion over here, the like this here, the hook is going to be mount, so that it is purely designed for bending stresses, and the diameter over here is should be the diameter of bearing, and this diameter is nothing but hook diameter. Okay, so we have to consider these dimensions started from here. Okay, so let's see how we can design it. So I request all, while designing this cross piece, you have to draw this diagram properly. Okay, so first of all, before starting to actual design, we will go with the bearing design. For hook, we need to design a gear bearing. As we know that hook is purely carrying the vertical load, that is only axial. So axial, or you can say thrust bearing, only thrust bearing is suitable for hook. So selection of bearing based on two criteria. First, bearing internal diameter, and second is a dynamic capacity. So we have selected a bearing series of 512 page number 4.27, that is SKF 51256, whose dynamic capacity is 1,63,000 kgf, and static capacity is 35,500 kgf, whose diameter D is equal to 280 mm internal, small, and bigger diameter is 380 mm, and height is 80 mm. So first criteria, or how we can solve, first criteria is the applied load is less than the dynamic capacity of bearing. So let's see how. So it is seen that the dynamic capacity of bearing is greater than the load carrying, that is value of Q. So it is safe for first condition. Now we are going for second condition. So first of all, we have considered a length of 500 mm, and in between that 80 mm diameter we have considered, that is total height of the bearing. So now we will see the maximum load which we will be carrying, as the bearing is continuously fully in contact with the trunnion surface, so that or you can say crossface surface. So we have considered the continue load over or cantilever beam over here. So equation for that, m max is equal to q by 2 into 350 by 2 minus q by 2 into 80 by 2. So putting all the values, and what we get, the maximum bending is 10.150 25 into 10 raised to 6 Newton mm. Now we have to calculate the width of the crosspiece. So W we have denoted uh, crosspiece width B suffix C so that we can identify which component width it is. So we have provided suffix C. So is equal to BC is equal to 380, that is a major diameter, plus twice multiplied by 25. So 380 is the maximum diameter of the bearing, plus we have keeping a 25 mm margin outside. So in this diagram I can show you where these margins are considered. So this is the diameter 380, and we are keeping this 25 mm and this 25 mm, so that uh, the length can be as minimum as possible, so that the optimum design could be occur. Okay, so total width which we have assumed is a 430. Let's see how it's sustained or not. So z is equal to I max divided by y, I xx divided by y. So I is equal to 112 BC minus 18 into HC cube divided by HC by 2. So we don't have a value of height. So we have considered the height of crosspiece in equation in the form of calculated the value of Z in the form of HC. So what we can get 58.33 HC square. Now next material for that, we have considered the material carbon steel for crosspiece with design sigma t value is 100 megapascal. So tau is equal to m max divided by z. So we know the value of sigma t m max. Now from that equation we can calculate the value of hc. So putting all the values, what we get, hc is equal to 41.66 mm. So the height, total height, that small hc is nothing but the distance of the bearing depth. Okay, so it's a below distance than the bearing depth. So we total height of the crosspiece we need to calculate. So capital HC, that is the total height of the crosspiece, is equal to a small hc plus groove depth. So in B, we are not considering the total height of the bearing. We are just only considering the 1/3 height, because we have to generate a groove. If we increase the depth of that groove, the strength of the crosspiece is get reduced, or it minimizes, so that with the constant of strength criteria also we have to consider, we have to just give the guide to the bearing, not we don't have to fit it properly. We have to just give the guide, because the total load applying are axial. So because of that load it will not move. Okay, so the 1/3 height of the bearing we have considered for groove, so that is sufficient for placing the bearing in a proper position. Okay, so 41.66 plus 1/3 of 80, what we get, 68.32. We are just modifying to 70 mm. Now next, trunnion diameter. So trunnion diameter is the outside supporting bars. What you can see, I can show you in a diagram directly. So these are the trunnion diameter which can be kept in the side plates, so that the crosspiece can be mounted properly. Okay, so again for trunnion diameter also we are considering the carbon steel with design sigma T value is 100 megapascal, tau is equal to 50 megapascal, and bearing pressure we are considering is 40 megapascal. So bearing pressure is equal to load divided by 2 divided by projected area, because it's we are considering from one side, so we are divided load in half. Uh, so Q by 2 divided by diameter of trunnion into the thickness of the shackle plate. Now here the shackle plate thickness we have considered is a 50 mm. Um, for putting all the values, what we get, the trunnion diameter that we have calculated is 37.5. We are modifying it to 50 mm by considering the factor of safety. Now we have to check this trunnion diameter for shear, because it is ultimately hanged in between, because the total continuous load is acting at the center, and because of that it could be shear in a shackle plates. So checking for shear, uh, load Q by 2 is equal to pi by 4 trunnion diameter square into the tau. So we know that value, all the values. So putting all the values, what we get, the tau value of tau, induced value of shear stress is 38.19 megapascal, and our design stress is 50 megapascal. So the design is safe. Now next component, design of shackle plate. Okay, so the whole cross piece assembly is going to be mounted in between these two shackle plates. um, we have considered the thickness of shackle plates is 50 mm, so that it can be easily withstand with the load. Okay, since the bearing diameter of the axle is greater than trunnion, uh, we consider the section 1 is a much weaker than the section 2. Okay, so in section 1 what we are applying, we are putting the bearing over here, and we need to calculate the width of the shackle plate. Now the load on the plate, because everywhere we have to give the support of the bearing itself. Okay, so that's why we consider on the load plate, load on a plate, that is a twice load of each, what you can say, 2F, that is a load per bend. Okay, so 2 into 43,393.6. So what we get, 86,778 kgf. Okay, so material selection, we are considering the carbon steel with this value of sigma T is 100 megapascal. Normally we are considering same material for all the component, so that the wear and tear get be uh, take care it properly. So 2F is equal to, now we have to consider the area. So what could be the area? So the total width minus the diameter of bearing, so that is a proper area, into thickness of the shackle plates multiplied by sigma T. We know the thickness which we have considered is 50. One more correction for here, you could change that this dimension is 2 to 5, because that bearing diameter based on trunnion diameter is 2 to 5. Okay, so putting other values, and what we get width is 220, so 2 to 4. So we are increasing that or modifying that width, that is 250 mm. Now center distance between two axles. So while calculating the center distance, we have to consider lots of things. So first of all, sheave outer diameter plus bearing height plus cover thickness plus twice inner washer thickness plus twice nut thickness plus 2/3 bearing height plus crosspiece height, half of crosspiece height. So these things we have to consider, but we don't know the value of sheave diameter. Generally, it is considered 30 times of the diameter of the rope or 20 times of the diameter rope based on if it is a power driven, then we have to consider capital D is equal to 30 times of the small d, and if it is a hand driven, then it's a 20 times of the small d by referring PhD page number 9.9. Okay, so our system is a power driven system, so we are considering 30 into 32. First criteria, capital D should be the equal or greater than 30 times of the wire rope diameter. So putting all values, that bearing height is 80 mm, cover plate thickness we are considering 3 mm, washer thickness we are considering 5 mm, then nut height we are considering 18 mm, then a bearing height which is 80 mm, that is 2/3, and the value of HC, that is a 160. So putting all the values, what do we get? The total shackle plate length is 1225 mm. Sorry, center distance between two axles is 1125. Now length of shackle plate. So LS is equal to twice into the bearing diameter plus the center distance plus the tunion diameter. So bearing diameter is 225. The center distance is 1225 and the tunion diameter is 50. So total length of the shackle plate is 1775 mm. Okay. Now next, design of sheave. So referring PhD page number 9.10, you can directly get these values. Let's see. Okay, so here all the values of the sheave diameter is sheave are given over here. Just we have to select the rope diameter, proper rope diameter. Okay, so we have a rope diameter. Uh, okay, look at here. So based on the rope diameter, D is equal to our rope diameter is 32, but in the standard it is shows the rope diameter is equal to just a minute. The rope diameter is equal to 32. Okay, but in the standard it is not a 32. It's a 34.5. So we have to consider this standard one, and you have to draw this diagram and note down these standard dimensions for that. Diameter we have already calculated based on the criteria. Okay, next one, next component, design of a rope drum. So referring PhD page number 9.2. Okay, so whole the rope diameter dimension with the diagram and formulas are provided over here. You just while designing this rope drum, you have to first of all draw this diagram roughly so that the examiner could get an idea what we want to do. Okay, and formulas are given at the left side. So it is very simple to design the rope drum. Okay, let's see how we have designed. So first of all, draw this diagram. Okay, next one, the first condition, referring page number 9.3, number of turns on the drum for one rope, that is z is equal to hi divided by pi t plus 2. Okay, so drum diameter is equal to sheave diameter, which we have considered, that is 960 mm or 96 centimeter. Transmission ratio is 2, that is I. H is equal to 10 meter, that height which is already given. So we have considered that could be converted into centimeter. Okay, so putting all the values, what we get z is equal to 6.63 plus 2, that is 8.63, which is equivalent to 9. So the number of turns on the drum for one rope are 9. So maximum 10 10 rotation or 10 rotations of the drum can be occurred to lifting the total load for a 10 meter. Okay, now next length of the drum, L is equal to 2hi divided by pi t plus 7 into s. Okay, s is a service factor, or you can say sorry, it's in a pitch. S is equal to pitch. Now for one rope we are assuming pitch is equal to 1.5 centimeter. So L is equal to uh, we know the diameter d, we have all the values, so we're putting all the values and we can calculate that drum diameter is 960. So converted into the centimeter, what we get, length is equal to 32 centimeter, that is 320 mm. Now let's check whether the wall thickness of the drum can be, we haven't calculated the uh, wall thicknesses and other dimensions of the drum, so we can calculate by referring page number 9.3. So generally drum is not manufactured on machine, it is a purely casting. So the cast material which we can refer from page number 1.4. So here the CI with the grade SG 800 by 2 is to be considered, with the value of sigma t, design sigma t is equal to 200 megapascal. Factor of safety is considered is a 4. Okay, referring page number 9.3, the wall thickness of drum W is equal to 0.02 d plus 0.6 to 1.0 centimeter. So here we are considering directly mid, or you can directly go with the 1.0 centimeter. So the calculations part could be very easy. By calculating all the, putting all the values, what you get, W is equal to 2 centimeter, that is a 20 mm, that is the thickness of the drum, so it can withstand the load. Now next one is a flange diameter. So flange diameter of the rope drum df approximately equal to d plus 6 times of rope diameter. So 96 plus 6 multiplied by 3.2, so the diameter of the flange is equal to 115.2 centimeter. Okay, so we have calculated drum values into the centimeter, that could be remind all of you. Then we have to check whether it can be sustained, the whatever the dimensions we have calculated, that can be sustained for a bending stress. So the maximum bending stress in a beam, the equation is given in page number 9.3. That is sigma b is equal to 8 into fr into L into D divided by D raised to 4, outer diameter raised to 4 minus internal diameter raised to 4 into pi. Okay, so internal diameter is outer diameter minus 2 times of wall thickness. So what we get, that is internal diameter is equal to 92 centimeter. Fr which is directly applied load, that is 16.5 ton. It is 1650 kgf. Now putting all the values of Fr, L, D, what we get, the value of sigma b is 9.7 megapascal, which is very less, as the design sigma b is 100. So uh, our design is safe. Okay, next one, looking for a maximum shear stress. So maximum shear stress, referring page number 9.3, equation is given 16 into mt into d divided by pi d raised to 4 minus di raised to 4. So all values we very well known. So putting all the values, we get the tau value of tau, that is shearing stress, is 23.3 megapascal, which is less than the design. So in both cases it is safe. Now next one, checking for the crushing stresses, as it is continuously in contact, or higher stresses are there, so there is a possibility of crushing. uh, Referring page number 9.3, for crushing states, sigma c is equal to fr by w into s, where s is a pitch. So putting all the values, what we get, sigma c is equal to 5.5 megapascal. So it is again where induced stress is less than that of design stress. So we will check for normal stresses, whether the normal stress is greater than uh, or not, or combined stresses are greater than the design tensile stress or not. So if that total stress is get lesser than the design one, then our design is safe. So total normal stress sigma n is equal to sigma b square into sigma c square. So putting all the values, and we calculated that sigma n is equal to 11.15 megapascal, which is very lesser. So this sigma n, that is total normal stress, we can use to calculate the combined equivalence stresses. So sigma equivalent is equal to square root of sigma n square plus 4 times of tau square. So equation is referring on page number 9.3. Condition is that it should be less than the design sigma t. Okay, let's see. So, putting value of sigma n and tau, what we get, the equivalent combined stress is 47.91, which is lesser than the design sigma t value. So our design is safe with respect to the drum. Now last part of the design is the selection of the motor. How we can select the motor? Referring page number 9.7. Let's see. Okay, for drum design, all the criteria or all the formulas are over here, so you can select it properly. So it's no need to what you can say by heart all the dimensions, all the problems. You just need to understand where the formulas are. Okay, so referring page number 5.124, you can calculate, you can find out the standard motors which we are using for industrial applications. Okay, so first of all, we need to calculate the motor power which is required. Referring page number 9.7, the motor power required HP is equal to Q into V divided by efficiency into 4500. As it is mechanical, we are considering the efficiency is 98%. The Q, we know that 1650 kgf multiplied by velocity 8 meter per second, and the efficiency, by putting all the values, what we get 2.99 HP motor size, multiplied by 746, what we get, it's 2.23 kilowatt. Now for selecting the motor, just let take a glance. So here they have provided the value in the form of kilowatt. All the standard values of kilowatt are provided here. So there are two types. One is a foot mounted and second one is a flange mounted. So we are selecting normally flange mounted for engineering application with a class E insulation of race, working on three-phase motor. So generally, if you have time permits, you can draw this diagram and you can just select the standard from the uh, required required uh, to satisfy the requirements. So our requirement is a 2.23 kilowatt. Now if you look at, it's a 2.2 and 3.7. If you have, it is the value is in between. if if you think your 2.2 watt motor able to sustain, but I preferred you don't go for 2.2, go for 3.7, so that uh, if sudden load is occurred or any additional load, it can be occurred, your motor will be able to sustain that load also. So selecting 3.7 kilowatt. So selecting 3.7 kilowatt with the motor RPM of 1500. You can just note it down, the basic dimensions and frame size and flange dimensions or designation, so that it can be easily, uh, we can easily recognize this motor. Okay, so that's all about the design of EOT crane. I hope from problem number 2 you betterly understood rather than problem number 1. Again, I will create one more design. In that, I will try to elaborate more and more so that you can understood more. Okay. So thank you very much. If you have any doubt, you can personally call me and contact me. Okay. So thank you very much.